Welcome back. In this short session, what I would like to do is derive the Fourier transform, which is discussed in our textbook in section 1 of chapter 7. Really what we're wanting to do is derive equation 7.8b based on what we already have learned in the previous segments of this class. Looking at equation 7.8, which is where we want to go, it's split into two equations. The first one is taking this non-periodic signal, x of t, and scaling that or weighting that by this complex exponential, e to the minus j omega t. And it's scaling that x of t for all time as it integrates time away. And it's trying to look at this waveform, this aperiodic waveform x of t, weighted by this complex exponential as a function of omega. If we picked a given value of frequency omega, maybe omega equal to 10, then we could have this rotating phasor e to the minus j10t that rotates as a function of time, and we're comparing that or correlating that with x of t for all time from t equal minus infinity to infinity in equation 7.88, and we're trying to say how strongly correlated is little x of t with that frequency 10. And that number is coming to us then as capital X of omega. And since we're scaling this by this complex exponential e to the minus j10t, capital X of omega could be a complex number. But its magnitude will essentially give us the size or the weighting of that little x of t's component at 10 radians per second. Equation 7.8b really sort of goes the other way. It goes from the frequency content of the signal, capital X of omega. From 7.8a, we get the frequency content of our signal. If somebody gives us the frequency content of our signal, capital X of omega, then we can actually weight over all frequencies omega. That's what this integral in equation 7.8b is doing. And weight that by the sinusoids e to the j omega t for all omega and build up the resulting aperiodic signal little x of t. These two equations allow us to go from the time domain to the frequency domain to provide us with the frequency content. That's the analysis equation, or we could synthesize this time domain waveform, little x of t, that's not necessarily periodic. We could build that up out of its frequency components, capital X of omega. We want to get a better feel for where these equations come from in this short derivation. And this is somewhat of a heuristic derivation, but our goal is to create for this little signal x of t, or not little signal, but an aperiodic signal. It's not periodic. We want to take this x of t and find how can we rewrite that as a combination of everlasting exponentials. Those everlasting exponentials are really just these complex exponentials, but they go on for all time, and that's going to give us the frequency content in little x of t. In particular, if somebody is providing us with little x of t, that's this, let's just hypothetically sketch something that is not periodic. There's x of t as a function of time. Again, just for emphasis, we're saying this is aperiodic or not periodic. I think it's clear that that's not being repeated for any length of time. And our periodic waveforms that we're used to seeing never really well, they have begun at negative infinity in time, and they just keep going until an infinite time into the future, from minus from t equal minus infinity to t equal plus infinity. And this one has a finite duration or interval of support. X of t is then not periodic. What we want to be able to do then is look at or try to answer the following question. How would you, now this is, I'm throwing it into your court, how would you expand or write or express this aperiodic waveform x of t into a collection where we've typically been, for Fourier series, we've just been summing up individual frequencies. Here we want to maybe take that summation to a limit and look at not a summation, but instead an integral. How can we integrate or combine a collection of complex exponentials in order to create or write little x of t in terms of that collection of complex exponentials? Anytime we are asked a question, a lot of times it's helpful to go back to what you already know. And in particular, knowing what we already know from this class. What do you already know how to do? And we don't have to think that far back. We're now in chapter 7. All we really have to do for an answer in terms of coming up with a way of expressing this aperiodic signal in terms of a collection of complex exponentials, really we only have to go back one chapter into chapter 6. Let's now remind ourselves from chapter 6 that that allows us to expand or write periodic signals into a sum of complex exponentials. What we want to do then is use that knowledge. Meaning the answer to this rhetorical question is yes. What we want to do then is connect this aperiodic signal, little x of t, to something that we know already how to do. And we already know how to write a periodic waveform as a collection or a sum of complex exponentials. Can we sort of trick ourselves or this process into accomplishing that goal? The idea then is to actually start with little x of t and now build from that a periodic waveform. And we're going to say that we're going to extend little x of t into a periodic waveform, and we're going to call that the process of periodic extension. Meaning, what if we created a periodic signal from this original aperiodic waveform x of t? As I said, we're going to call that a periodic extension, which now looks like the following. We had to begin with this x of t. What we want to do is go outside of where it's non-zero and say, you know what, I'm going to go over here, and when it stops, I'm going to go a little beyond that and say that's, well, if it wasn't symmetrical, I would need to go to the larger side of the asymmetry and call that distance, let's say t naught over 2. And then I would come back over here the same distance, and now I have identified one period of an interval, or an interval of one period. Now that I've done that, I can now go over here to t naught. I can actually go here to minus t naught, and I can start copying this functional form of x of t to where now I've produced a periodic extension, which I will call something else. It's no longer quite little x of t. It's now little x sub t sub 0 of t, and I need this to be periodic, and I can pretty easily do that without spending all day drawing these pictures or copying the little x of t periodically at every point t naught. I can simply do these three dot dot dots on the left and right of this waveform. Now I have a periodic waveform. Once I have a periodic waveform, or you have it, now we can actually write this or find the Fourier series of little x sub capital T sub 0 of t. We now simply have to remember what the Fourier series expression was for complex exponentials, or using the complex exponential form of the Fourier series. That's an infinite sum, and again we allow for positive and negative frequencies to produce real values for the expression capital or little x sub capital T sub 0 of little t, and those sines and cosines are weighted by a possibly coefficients that are complex. And here is then our rotating phasor, and we now have some fundamental period omega naught, which is based on t naught. This is, now that we're in chapter 7, this is now equation 7.1. But it's what we've been using in chapter 6 when we had a periodic waveform in the complex exponential structure. If we wanted to now pull out of this representation for little x sub capital T sub 0 of little t, really all we would have to do is restrict our attention in a real world setting to the portion of this x of capital T sub 0 of t naught that falls between our interval of interest, which is minus t naught over 2 in time, to plus t naught over 2. That's what I want to say here in this thought statement. We could find the answer, so these coefficients, capital D sub n, for all of these harmonic frequencies in omega naught, we could find equation 7.1 and then just neglect the part of x sub t sub 0 of t that lies outside of our interval of interest, which is our interval of interest. We've now identified it to be from minus t naught over 2 to T naught over 2 in time. Remember, though, in this complex exponential Fourier series expansion, how we have defined these coefficients, capital D sub n. D sub n just weights each of the different harmonic frequencies in this representation. And D sub n, let's just recall what that looks like. In that equation, we need to figure out what capital D sub n is. And D sub n is now this integral of the periodic waveform, which is the periodic extension of what we started with. We only need to examine this over one period of time, and we divide out the time. That's the 1 over T naught. We weight it by these complex exponentials at the different harmonics in omega naught, and we integrate over one period of time, so our variable of interest, or our variable of integration is little t. This is in the textbook equation 2a in chapter 7. That's now an expression for each of these coefficients, capital D sub n. We are again trying to find a way to write the frequency, or identify the frequency content of little x of t, not this periodic extension. But remember, x, this periodic extension, how we defined it, x sub t sub 0 of t, and the original non-periodic signal, x of t, we could make those equal if we simply allowed our period that we picked that period. If we would let that period go off to infinity, those two expressions would be equal. If we let T naught go to infinity, then we have this general expression for D sub n. D sub n is now 1 over T naught. Again, we're letting T naught go to infinity, meaning we can now integrate from minus infinity to plus infinity. Those limits at one point were just minus T naught over 2 to plus T naught over 2. As we let capital T naught go to infinity, little x sub t, capital T sub 0 becomes little x of t, and we have e to the minus j in omega naught t. And again, we're integrating with respect to time, dt. This is equation C, or 2c, in chapter 7. This expression for these coefficients helps us come up with a slightly modified expression that captures the frequency content of our waveform little x of t. Because we're now dividing by 1 over T naught, maybe that is not very comforting because we're letting T naught go to infinity. Let's now define a new quantity, which is a function. Let's define a new function that's based on this expression above in equation 7.2, based on this D sub n structure in 7.2c. And what we're going to do is allow omega to be continuously variable and not worry so much about the harmonics in omega naught, or you can think of in omega naught really, really getting small, and so now we're just smearing these individual frequencies into a continuum of frequencies. Let's now define a capital X of omega, and this is going to represent the frequency content and little x of t. Let's forget about that capital T scaling of 1 over t naught, and now we just want to integrate little x of t weighted by this complex exponential that is allowed to vary for all continuous frequencies omega, and integrate that over all time. This omega is now a continuous frequency variable. And in this particular expression, we are actually integrating over all time, and that allows us now to examine the frequency content, or obtain the frequency content of our aperiodic signal, little x of t. We're integrating over all time to analyze the frequency content in x of t. We want to now find an expression for little x of t. And to do that, let's now make some observations, or an observation relative to what we've just defined to be this new function, capital X of omega. If somebody now gave us this frequency content, let's say this is now our X of omega. Here's DC. This is now frequency axis omega. That's our independent variable. Now what we want to do is actually break this up, or sample this. So we're reintroducing this frequency space, but now and we just keep doing that at every omega naught. What we're wanting to do now is, from this capital X of omega, this new function that we've defined, let's go ahead and examine it at integer values of some frequency omega naught. And we're then really just sampling in the frequency space. Remember, our independent variable is omega. We're sampling in the frequency space this new expression that we just invented, this capital X of omega. Or you can think of it as we're now selecting points in the frequency space. And we're being very precise in how we're doing that. We're looking at the same spacing for each of these locations in frequency, omega naught, 2 omega naught, 3 omega naught, etc. If we now sample capital X of omega in frequency, we now are looking only at specific values, capital X of n omega naught, meaning we're now replacing this continuous variable omega with this sampled version, little n omega naught. We have the integral from integrating over all time from t equal minus infinity to infinity, x of t. We have now our complex exponential, but now we only are worried about discrete frequencies, little n omega naught, t dt. But that looks very, very familiar. That is essentially d sub n if we simply scaled that expression for d sub n by t sub 0, and then we would have exactly this particular picture that we're used to. Meaning now we can express capital D sub n. Remember what D sub n was? That was our coefficient weighting on each of these sinusoidal complex exponentials that we are interested in. That's now in terms of this new function that we created, capital X of n omega naught over T naught. Or that's just a scaled version of this sampled new function that we created, capital N of n omega naught. We have a scaling factor of 1 over T naught, and capital X of n omega naught is just this sampled value of what we defined to be capital X of omega. Let's just remind ourselves of what capital D sub n was. I already have said what that was, but let's just explicitly write it down. Capital D sub n are these Fourier coefficients, and because it's subscripted by little n, these are these Fourier coefficients associated with the nth harmonic, or the nth harmonic is just n omega naught. We now have a way of relating capital D sub n to this new function that we defined, capital X of omega, that we've now sampled, and we want to end up with frequency content in this aperiodic signal, little x of t. And to make little x of t look like little x of capital T sub 0 of t, which was the periodic extension of little x of t, we want to let t naught, the period, separating those copies of little x of t, we want to stretch that out and push that all the way to infinity. And that now allows us to look at aperiodic signals. If we never repeat, which is what's going to happen if t naught is going off to infinity, we are then really looking at non-periodic or aperiodic signals. Remember what or how the frequency in radians per second is related to t naught. If I ask you to give me omega naught, that's 2 pi f naught, or 2 pi over t naught. As we let t naught go to infinity, this omega naught is getting smaller and smaller, or it's actually going to 0. We now have finer and finer frequency resolution. Let's now use this new expression for capital D sub n in our complex exponential Fourier series expansion of this periodic extension little x sub t sub 0 of t. That was now just this sum from n equal minus infinity to infinity. We have a Fourier series for the periodic extension times d sub n, but d sub n, remember, was x of n omega naught over t naught, and that's now scaling or weighting e to the j n omega naught t. That's now our periodic extensions complex exponential Fourier series expansion in terms of, or rewritten in terms of, this newly defined functional form, capital X of n omega naught, the sampled version of that frequency content in this original aperiodic signal, little x of t. What we want to do now is actually let T naught march off to infinity to create an aperiodic waveform. And in that process, we've already said that as T naught marches off to infinity, omega naught's going to go to 0. Well, let's go ahead and let that become infinitesimally small, or go towards some delta of omega. What we're doing, or what we're saying then, is we could think of our frequency space. We had defined a way of sampling capital X of omega, but now as T naught goes to infinity, this is going to get closer and closer to 0. And as it does that, then we're just going to say, let's call that delta of omega, which is 2 pi over T naught. Or if we need to replace T naught in our derivation, we can write that in terms of delta of omega as T naught is 2 pi over delta of omega. Let's now use this T naught, capital T naught expression in there, in our expression for the complex exponential Fourier series expansion. We now have little x sub capital T naught of t. That's now equal to this summation from n equal minus infinity to infinity of x of n delta of omega over capital T sub 0, but we're going to replace that with what it's also equal to, which is 2 pi over delta of omega. And now that's what weights each of these different frequency components that are introduced by these complex exponentials. This piece in the square bracket is really the amount of frequency component in each of the harmonics, which are given by n delta of omega. Now, by definition of this periodic extension, we can make it look like little x of t, the aperiodic waveform, by letting that t naught go off to infinity. Now, what I'm going to do in this process is I'm going to go ahead and let this term in the denominator of the denominator, I'm going to allow that to slide up stairs, which is an equivalent location for that delta of omega. Now, by definition of this periodic extension, little x sub capital T sub 0 of t, we can now build or find or obtain the aperiodic waveform if we simply let T naught get infinitely large in the periodic extension, little x sub capital T naught of t. Let's do that now in this right-hand side expression. And notice that that 2 pi in the denominator does not contain time, it doesn't contain n. We can slide that 2 pi outside the summation, meaning we can now say this is 1 over 2 pi times the limit, and as t naught goes off to infinity, equivalently this delta of omega, this small frequency interval, delta of omega, is going to approach 0 in this infinite sum as n varies from minus infinity to infinity of x of n delta of omega. What else do we have? We also have the e, the complex exponentials, e to the j n delta of omega t, and let's not forget that delta of omega. Let's now see if we can put all of those pieces in. We now have e to the j n delta of omega t, delta of omega. Now, as we let delta of omega go to 0, delta of omega becomes d omega, the differential. And as delta of omega gets really, really small, n times delta of omega, we might as well just let that be a continuous variable omega. Meaning we can now relate this little x of t and set that equal to 1 over 2 pi. And as we chop up this delta of omega into smaller and smaller pieces to become d of omega, that summation now becomes an integral from minus infinity to infinity. And again, we're varying, little n actually causes us to vary with respect to frequency. Capital X of n delta of omega is now merging into or morphing into a continuous frequency variable omega. That now gets scaled by e to the j, and again, n delta of omega becomes the continuous frequency omega. T we don't need to worry about, that stays the same, and we now have delta of omega becomes d of omega, the differential. And this is now equation 7.7 in the book. We now have derived an expression for building up this aperiodic signal, x of t, out of a everlasting collection of complex exponentials, e to the j omega t. This is now what I like to refer to as the synthesis equation. And that allows us to actually build the signal x of t from its frequency content. Meaning if somebody told us the frequency content in a signal, they would be giving us capital X of omega, then we could plug that capital X of omega into this integral expression, scale it by all of these complex exponentials over all frequencies. Omega now we're integrating from minus infinity to infinity. Scale it by 1 over 2 pi, and we will actually produce or synthesize our waveform of interest, little x of t, the aperiodic waveform. And remember, we built or defined capital X of omega initially. We said, oh, let's just, based on capital D sub n, let's create this new function, capital X of omega, and that's actually our analysis equation. That now tells us the frequency content in our aperiodic signal, little x of t, by seeing how it's correlated with these complex exponentials, which are really giving us the frequency content in the signal. This is now the pair of equations. Capital X of omega now tells us how little x of t is, or what its frequency content is as a waveform. And what we now have available to us is the ability to go from the time domain into the frequency domain to obtain the frequency content of the signal. And we also, once somebody gives us the frequency content, which is a frequency domain concept, we can now build the time domain waveform, which is no longer restricted to being periodic. It can now be aperiodic. That now completes our derivation of the Fourier transform, and what we want to remember is that now we have these two equations that are paired up that allow us to relate time domain to frequency domain and frequency domain to time domain, so that we can now think in both domains, and that gives us a much better way of intuitively thinking about these concepts.